Hello everyone, this is Dr. Tasadduq Hussain and I am ready with another lecture. I hope that you guys have checked my previous lecture. This lecture is probability curves, wherein we will learn about the radial wave function and the angular wave function, which gives us the shapes of s, p, d and f orbitals. We looked at the difference between the psi and psi square, and now the next section of our lecture is the probability curves. So the probability curves are divided into two parts. One is the radial probability and the another one is the angular probability. So this RR is radial probability and this theta and phi are the angular probability. Okay, so first we'll go with the radial probability and we'll see how we can use this radial probability to find an electron in an atom around the nucleus, and this distance will keep as r. When we plot this radial probability, that's r, against the distance or the distance at which an electron can be found in this atomic orbital. So I have three different orbitals here. First is 1s, 2s and 3s atomic orbitals. For these plots, you will see in case of 1s atomic orbital, I am plotting radial probability R10, that means n, that is the principal quantum number or the principal level is 1 and the azimuthal quantum number L is 0 for 1s. So when I'm plotting R10 against the distance at which an electron can be found around the nucleus in an atom, so I get this kind of curve. So this becomes 1s. However, in case of 2s, you will see that the probability of finding an electron is moving towards the negative axis, and the same is happening in case of 3s. Since I have already told you that in case of the probability curves, when we are trying to find the probability of an electron, in case of psi we get different values, so we can get plus, minus and 0 values. So for an electron probability, plus and 0 are acceptable, but this negative value, this is unacceptable. Now in case of the psi, we are getting the negative values. That's why I said that psi is not significant, it's non-significant. But if I square this psi, then in that case we get positive or 0 values, and those values become acceptable. So that's why we do the squaring. So I'm squaring this radial probability for same 1s orbital, and the curve that I'm getting is this one. And then for the 2s atomic orbital, when I'm doing r square for second shell and as with an azimuthal quantum number 0, I am getting this kind of curve. This curve shows me that the probability of finding an electron in 2s orbital is always positive. It's always positive here, and it goes to 0 somewhere here, and similarly it goes close to the nucleus. That means the probability is decreasing at these points, and these points we call them as nodes. So node is a place where the probability of finding an electron is 0, whereas these peaks are the regions where the probability of finding an electron is maximum. And if you have to calculate the number of nodes for a particular atomic orbital, so you calculate it by using the formula n minus L minus 1. So it gives you the number of nodes. So for example, if I have to calculate the number of nodes for the 3s atomic orbital, for 3s the n is going to be 3, azimuthal quantum number is 0 and minus 1, so that gives us 2. So that clearly indicates that there are 2 nodes in case of 3s atomic orbital, and there is 1 node in case of 2s atomic orbital and 0 nodes in case of 1s atomic orbital. This r is the distance or the distance at which the probability of finding an electron changes according to this curve. Now since we discussed about the radial probability, we have to discuss about the angular probability also. But before discussing the angular probability, I want you to introduce to a thing where you can see that if we consider an atomic orbital, and this atomic orbital is always going to be in a 3-dimensional space. So when we consider a 3-dimensional space, in case of 3-dimensional space, we have to always take into consideration the volume of a sphere, and we know the volume of a sphere is pi r square. always of a thickness dr. And in my previous section I already have shown you that if I take the integration limits from r0 to rr, that means from the starting position of the nucleus to the edge of this sphere, in that case the probability distribution or the radial probability is going to be r square NL 4 pi r square dr. Now if I use this equation and then try to draw the probability of finding an electron in this spherical shell, in that case we'll get the curves, the radial probability curves, in these forms. Okay, so for one s atomic orbital we are going to get the 4 pi r square 1 0 versus the distance of the electron, or the distance of finding an electron in an atomic orbital in this bell-shaped curve. And for 2s atomic orbital the curve is going to be like this, and for 3s atomic orbital the curve is going to be like this, and the number of nodes are going to stay same. Like 3s, for 3s you have 2 nodes. You can see there are 2 nodes in case of 3s and there is 1 node in case of 2s. Also, if you want to see what's the maximum distance at which the probability of finding an electron is maximum in this spherical shell, then you have to look at the peak area, and then this distance from here to here, this is going to be the minimum distance at which an electron can stay. And for hydrogen atom we know this is 0.529 angstrom. The angular probability always gives us the shapes of different types of orbitals, and we know the orbitals are of s, p, d and f, that's sharp, principal, diffuse and fundamental orbitals. So for s orbital we know that the azimuthal quantum number L is always equal to 0, the magnetic quantum number is always 0. For p we know L is equal to 1, m is equal to 0, or it can have plus minus 1 values. For d we also know that the values of m can vary from plus minus 1, plus minus 2 to 0, and the L has a value of 2. So this equation, that's the angular probability equation, this t and phi, that's the theta and phi, this can be written also in terms of this equation. That means that this theta is dependent upon the azimuthal quantum number and the magnetic quantum number, and phi is also dependent upon the magnetic quantum number. In my previous lecture from the Schrodinger's wave equation, I have shown you that the Schrodinger's wave equation can have different types of solutions, and upon solving the equation for an hydrogen atom we can get, for example, this equation. And when I try to solve this equation, which is a very complex process, I basically get these kind of values that I have mentioned here. So if I try to solve this theta for n and L, that is 0 and 0, I'll get this value, that's 1 by under root 2, and similarly for phi 0 I'll get a value of 1 by under root 2 pi. And by using these values and also the values that I get for the different types of quantum numbers on which these are dependent, I can deduce, or I can know the shapes of different types of atomic orbitals. So now let's see how we can use this angular probability to predict the shape of an atomic orbital. So this is for an s orbital, and these two values are for p orbitals actually. Okay, so now let's try to deduce the shape of s orbital. So from this equation we know that the product of these two, now we'll be looking, we are not looking at the radial probability right now, we are looking at the angular probability only, because we are trying to deduce the shape of an atomic orbital. So in that case I will take this region into consideration, or this region into consideration, and I will that's the product of these two gives us the angular probability. In case of s orbital, the values of L and m are 0 and 0. Okay, so they are mentioned here. So in case of s orbital, the values of L and m are 0, 0. So for theta, the values of L are 0, the values of m are 0, multiplied by the value of phi. But the value of phi is dependent upon m, so m has a value 0 in case of s orbital. Right? So this is the angular wave function, or the angular probability for the s orbital. Now since theta 0, 0 is equal to 1 by under root 2 multiplied by this phi 0 is equal to 1 by under root 2 pi, right? So when I try to solve this, this becomes 1 by 2 under root pi. Okay, so this equation that I obtained for the s orbital, so this is for s orbital actually, and this equation shows that the angular wave function is independent of the angles of theta and phi. So in this case, the angular wave function is independent of the angles of theta and phi. Theta and phi are the two angles. So that means the s orbital is always going to be symmetrical in shape. So if I try to draw s orbital, so if I try to draw an s orbital, it's always going to be symmetrical in shape like this in all the axes. So this is x, z and y axis. So this becomes s orbital. That's why we always say that the s orbitals are non-directional and they are spherical and they are symmetrical. So this concludes the s orbital shape. Similarly, we will look at the p orbital shape also. For p orbital, we know the values of L and M here. So for M, we have around 3 values. So we can have for M, we can have values 0, -1 and +1. And for L, we have 1 value. That means we have a total of 4 value. And we have to look at the different combinations that are possible to predict the shapes of the p orbitals. So the 3 possible combinations that are going to be here are going to be L is equal to 1, L is equal to 1, L is equal to 1. And then for M, it's going to be one case it's going to be 0, and the another case it's going to be -1, for another case it's going to be +1. So that means there are 3 different combinations that are possible for p orbitals. That's why the p orbitals has 3 suborbitals. And we know those orbitals are called as px, py and pz, right? So p has 3 suborbitals. Now we also know that the p orbital has a dumbbell shape. It has a dumbbell shape. And how we know that it has a dumbbell shape? We use these values and the values of this t and phi, that's theta and phi, in this equation, that's the angular probability, and we arrive at the conclusions that the shape of the p orbital is a dumbbell. So if I try to draw it on an x-axis, it's going to be like this. So this becomes px. In a similar manner, the py becomes like this, and then pz becomes like this. This is pz orbital. And the reasons for labeling these p orbitals as px, py and pz is that when you try to solve these equations, that's the angular wave function for the p orbital, it is going to have 3 different suborbitals, right? So let's try to solve this equation. We'll see how we arrive at the 3 different orbitals. For the first case, L is 1 and M is 0. In that case, this theta 1 0 and phi is also going to be 0. The values are going to be, for theta 1 0, I know the values under root 3 by 2 cos theta, under root 3 by 2 cos theta, right? And then for this phi 0, our value is 1 by under root 2 pi. So I have to product these two to get the angular wave function, and when I try to solve both of these, I get under root 3 by 4 pi cos theta. So this value is a real value, or it's an eigenvalue. So eigenvalues are acceptable to us, and when I try to plot this eigenvalue on the on the graph, then you see that we always get a dumbbell shape. If I try to plot this equation in terms of Cartesian coordinates, this becomes function of z, and when this angular probability becomes function of z, we label that orbital as pz. In a similar manner, when this angular probability becomes a function of py, we call it as py orbital. And in case of the angular probability being dependent upon the x-axis or a function of x-axis, we call it as px. So in this case, if I try to convert this equation into the Cartesian coordinates x, y and z, this angular wave function becomes under root 3 by 4 pi cos theta. And this cos theta, when I try to solve this cos theta in terms of the Cartesian coordinates, it becomes under root 3 by 4. This cos theta in case of Cartesian coordinates is equal to z by r. Okay, it's dependent upon the z-axis. So that means this angular wave function, in other words, is dependent, or it's a function of z. So that means the p orbital has a dumbbell shape and it's dependent upon the z-axis. Then for other two cases where you have -1 and +1, you will get it as a function of py axis and pz axis, right? Py axis or px axis. So that's why we have px, py and pz. Now looking at the shape of the d orbital, we know for d orbital we have 5 different values. Why? Because for d orbital L is always equal to 2, and for m we have values 0, and then we have values -1, L is equal to 2, then we have values +1. Similarly, L is equal to 2 and m is equal to -2, and then another value for this d orbital for the quantum number is +2. So in an overall we have 1, 2, 3, 4, 5 different values. That means the d orbital has 5 suborbitals. And we also know the names of those orbitals. The names of those orbitals are dxy, dyz, dzx, right? And then we have dx square minus y square, and then we have dz square. So these are the names of the 5 different orbitals that the d orbital has. And in a similar manner as I have shown for the p orbital, that the angular wave function is dependent upon the, if the angular wave function is a function of x-axis, then we call it as px. If it's a function of y-axis, we call it a py. If it's a function of z-axis, we call it a pz. In a similar manner for d orbitals, the shape is a little bit complex. It's a double dumbbell, and for double dumbbell it has to be dependent upon the, you know, 2 axes simultaneously. So for dxy, the angular probability is a function of, or it's a function of x and y axis. It's a function of y and z axis, it's a function of z and x axis, and the shape of this double dumbbell orbital can be drawn like this. This shows the shape of, you know, d orbitals. Which d orbital this is? So if this is y, and if I consider this as z, so this becomes dzx. So I'm just drawing the shape of one dzx orbital, that is dzx. The others you can draw yourself, and for this you get the negative values for the here, and these lobes are positive lobes. This is in a 3-dimensional space. So this shape is called as the double dumbbell shape. So now we have seen that the probability curves, and we have seen the radial probability, we have seen the angular probability, and with angular probability we try to deduce the shapes of the sharp, principal and diffuse types of the atomic orbitals. For fundamental it's more complex. So I think that pretty much wraps up my lecture for today. That's the atomic orbitals and their shapes. I hope that you guys liked this lecture. If you did like this lecture, then please subscribe to our channel and do share.